Okay, so we talked we talked about the simplest kind of surfaces in the space, just about flat planes. Let's talk about more interesting surfaces. So let's talk about surfaces. Well, a typical surface will be given to you. Well, we'll talk about curved surfaces, some kind of funny shapes. A typical surface will be given to you by some equation, some dependence between x, y, and z coordinates. And then the question is, suppose they are given an equation, some particular equation. How can you, sketch how this surface looks like? How can you imagine even how the surface looks like? The answer is, we kind of know how to sketch planar curves. Well, we have some tools. We looked at some equations in the plane. We know how to find maximum of something, how to sketch the graph of some function in the plane. Now we can use this knowledge to sketch something in the space. So the general idea is, suppose you are given some surface. You don't know how it looks like, you just know an equation. Well, try to look how the sections of this surface look like. Suppose you want to fix something like x coordinate is equal to 5. So I'm looking at this particular plane. I have my surface. When I plug in x equal to 5, I get some equation about just y and z coordinates. In this plane, I have some dependence between y and z coordinates. I will be able, hopefully, to sketch this. Now I'll have a section of my surface on this plane. I'll continue. I have the section when x is equal to 5. Take a step, look at the plane x equal to 6. Try to sketch this section, take a step, sketch a section. Take a step, sketch a section. And now when I have lots of sections like this, I will try to imagine how they connect to each other. And that will be roughly a shape of my surface. So the idea is, so we'll try to sketch surfaces by investigating their traces. Traces are just sections by planes which are parallel to the coordinate planes. So these are sections by planes of this kind. You fix one of the coordinates and you look what is the remaining dependence between the other two coordinates. So this idea is kind of, abstract. It can be only really understood on particular examples. So let's try to sketch a couple of surfaces. First example. Sketch the surface x squared plus y squared is equal to z. So here's a surface. Well, it's some equation. It's tried some dependence between the coordinates x, y, and z. What kind of shape does it define in the space? What is the set of all points x, y, and z which satisfy this equation? Okay, so let's start. We'll try to take sections. Let's say, let's start with kind of xy traces, which means let's cut the surface by planes which are parallel to the xy axis, to the floor. So xy traces. So I want to fix a certain height. I want to look at this surface at the height z0. Z0, think about Z0 as of some number, something like 5. So what is this shape? If you look at the equation x squared plus y squared is equal to some number, what is this shape? Now, this Z0 is not the height, it's not the third coordinate, it's just some number. What kind of shape is described by the equation x squared plus y squared is equal to some number? Let's sketch it. X, y. Yeah.
Circle.
A circle. A circle of radius square root of z, of Z0. So it's a circle with radius square root of Z0. Well, it kind of works. It only works when Z0 is positive. So we write this for Z0, which is positive. It is a circle of radius square root of Z0. Okay, so we understood quite a bit already about this surface. Yeah.
What is 4? Is it 4? 4x. Is this 4?
4. Yes. So when Z0 is positive, 4 positive Z0. So we actually understood quite a bit about this surface. We know that horizontal cuts of this surface are actual circles. So this surface is kind of a bunch of circles stacked on top of each other. Well, of course, there are lots of different ways to stack circles on top of each other. You can take such a circle, expand it, and get some kind of such a shape. You can take such a circle, expand it, then contract it, then expand it, you get kind of vase like this. So there are different ways to stack circles on top of each other. But we already understand something about this. Let's look at other sections. Let's look what happens if we cut the surface by not horizontal planes like this, but rather vertical planes like this. So let's talk about, let's say, XZ section, XZ planes. I now look at the same equation, but now I think about y being fixed. X squared plus y naught squared is equal to z. Now I'll sketch the set of points x, z, which satisfies such an equation. What is the set of points z, x, z, which satisfy an equation of the form z is equal to x squared plus some number squared? How does it look like? Think about the equation z is equal to x squared plus 25. What is it? What is the shape? It's what? Parabola. Yes. It is a parabola. It is a shape like this. And this y naught squared appears right here. When x is equal to 0, z is equal to y naught squared. It's in this distance. So in fact, all the sections by such vertical planes are parabolas. So if you look at this surface kind of in this way, you see a bunch of parabolas which are stacked in front of each other. Parabolas which go down, up, down, something like this. Okay, we are almost there. Let's continue and talk about YZ planes, YZ creases. So we already know such sections, Let's talk about such sections. X equal to x naught. Well, it's quite similar. We are talking now about equation of such form. X naught squared plus y squared is equal to z. They are still parabolas. If z is equal to y squared plus some number squared, still parabolas. Okay, now the somewhat hard part. I want to try to imagine how this whole thing fits in three-dimensional space. So we kind of touch this surface from different directions. Now I want to understand how it fits in three-dimensional space. Well, so what do I know? I know that the horizontal sections are circles. I know that the vertical sections like this and like this are both parabolas. So let me sketch a couple of parabolas. Let's say this parabola in the YZ plane. I have another parabola in kind of in XZ direction. And the whole surface should be made out of circles. So horizontal sections should be circles. So here's the shape. If you cut it by such planes, you get parabolas. You see this parabola. If you cut by a plane which is a little bit closer to me, you'll see such kind of parabola which is even higher, and so on. If you cut it in this direction, you'll see such parabolas. If you cut it in horizontal direction, you'll see circles. So it's something which in one section looks like a parabola, in another section looks like a parabola, and otherwise it's kind of a bunch of circles which become larger and larger. So that's the shape. This shape is called a paraboloid. It's actually quite an important shape. Well, it's important in mathematics for reasons which we'll see a little bit later. It's very important in kind of engineering. If you want to build a satellite dish, you always make it in the shape of paraboloid. Paraboloid has a very special property. If you look at a bunch of parallel rays which come from above, if they get reflected in the paraboloid, they all come together into just one point. So it's very important for optics, for building satellite dishes. For now, for us, it's just an example of sketching a surface. So here's an equation. We started with an equation which is just, well, a formula. You don't really see what it means. After we tried to play with it, we cut it by different sections. We found out that it is actually this shape. Okay, so maybe any questions about this? Yeah.
On your x and y traces, like the y naught squared intersects the axis there above x, but so how come in the final diagram it looks like it's
So
finished
here,
at origin like that?
take another sketch. So I have my paraboloid, a shape like this, or continuous like this. If I cut it by a plane which is, well, parallel to the plane of the board, well, there is this parabola, this one, the kind of the one which is the plane of symmetry of this paraboloid. This corresponds to when y naught is equal to 0. If we cut it by the plane, sorry, if we're talking about y equal to something, then you should imagine such planes. So there is this parabola, y equal to 0.
Right.
Then you can cut it by different planes which are parallel to this. Let's say I try to cut it by y equal to 1. I'll get a parabola, but this parabola is not going to pass through the origin. Next one will be, let's say, y equal to 2. The height of this vertex of the parabola will be now y naught squared, which is 4. So this distance is y naught squared.
Understand.
And this is y naught. Yeah?
Would we ever have to see a cross-section of it from a plane that is not parallel to x, y, or z?
Well, in our course, no, just because we are trying to do some simple examples. In general, if a surface is naturally aligned with some direction which is not one of the axes, like imagine such a paraboloid, but the axis, such a vertical axis is not vertical, it's kind of rotated in that direction. Then yes, it would be natural to cut it by such planes. But then the equation is going to be much more complicated and we will not have such examples in the course. Other questions? Okay, let's talk about the different surface. It will also be quite important for us later. It has a similar equation, but you'll see that the surface will be quite different. So the equation is x squared minus y squared is equal to z. So let's talk about this surface. I'll do the same trick. I'll describe xy traces, then xz traces, and yz traces. For xy traces, I will be cutting by horizontal planes, z equal to z naught. But now the shapes become more interesting. What is this equation? X squared minus y squared is equal to some number. So think about something like x squared minus y squared is equal to 1. What is this equation? Yeah.
It's an ellipse.
An ellipse? No. So an ellipse is an equation x squared divided by some positive number plus y squared divided by positive numbers is equal to something. This is not. So this number is negative. Okay, so maybe we don't recognize this curve. Well, it's a little bit sad, but well, let's try to imagine how it looks like. So let me, on a separate board, try to sketch the curve x squared minus y squared is equal to 1. So I can rewrite this as x is square root of 1 plus y squared. Well, I will probably have to write that it's either a positive or negative number. And then let's try to understand how the picture looks like. When y is large, something like 1,000,000, x and y are more or less the same. So you take 1,000,000, you square it, you get 1 and 12 zeros, you add 1, so you barely change it, and then you take the square root. So you get more or less the still 1 million, maybe a little bit larger. So when y is large, you get that x and y are almost the same. So x is just a little bit larger. So you get something here. Well, or negative. When y is not as large, well, you see that x is a little bit larger than y. It's never smaller than 1. It's square root of 1 plus something positive. So when y is equal to 0, you get x equal to 1. And otherwise, well, it's a little bit larger than y. So you get something of roughly this shape. And also when x is negative, or x could be negative, you get something like this. So admittedly, I didn't justify quite a lot of things. I didn't justify that there are no local maxima, local minima, but it is true. This shape looks like this. It's called a hyperbola. It's a shape which is kind of defined by two lines which are called the asymptotes. And this shape kind of approaches this asymptote to infinity and otherwise makes such a thing. It is, once again, a shape which is interesting not just in mathematics. If you look at a comet which comes to the solar system just once and leaves it forever, you can be sure that it goes in such a trajectory. It's a hyperbola. So it is quite an important shape. So let me just sketch this thing. It's a hyperbola like this. This picture is correct when the node is positive, strictly positive. When the node is negative, you'll get quite a different picture. You'll get that x is actually smaller than y. So your hyperbola will lie not on this side of these lines, but rather on this side. So when the node is negative, you'll get a similar picture, but more like this. Unfortunately, we are not done yet. Even though we try to visualize one set of sections, horizontal sections, well, even this wasn't that simple, but still, let's say that we kind of managed to do this. Let's try to visualize other sections. X, Z sections, and Z traces. What kind of curves do we get now? Well, let's look at the equation. It's x squared minus y naught squared is equal to z. This is much simpler. So z is x squared minus some number. Well, it's a parabola. It's a parabola like this. This is minus 1 squared. So at least in this direction, y equal to y naught, in such planes, we are talking about a bunch of parabolas. Okay, and let's talk about xy traces, yz traces. We fix x to be some number x naught, and we see such an equation: x naught squared minus y squared is equal to z. Now z is some number, or some number squared, minus y squared. What kind of shape is it? Okay, almost. So it is the same in the sense that it is also a parabola, but there is a small difference. It faces down, exactly. So it is something positive, it's not squared, but now minus y squared. It's a parabola that faces down. Okay, so now we are facing f.
So is that point x not squared, or is that area between?
It's not squared, it's this distance
Oh.
from the origin to the vertex of the parabola. Okay, now we see how the sections look like. Now we are facing the admittedly complicated problem of fitting everything together. You have a bunch of parabolas like this on such planes. So imagine a bunch of parabolas. You have a bunch of parabolas facing downwards on such planes. So we have parabolas like this. And in this direction we have hyperbolas, like this or like this. So maybe let's try, let me try to wave my hands first and then produce a picture. Let's think about the plane x equal to 0. So imagine this board being the plane x equal to 0. On this plane, let's say that these are the axes, y-axis and z-axis. So on this plane I see an inverted parabola, z is minus y squared, something like this. Okay, now think about this plane. This plane is y equal to 0. On this plane I see y equal to 0, a parabola which faces upwards. So from here, imagine a parabola going upwards. So once again, a parabola facing down in this plane, a parabola facing up in this direction. Let's move this plane to the side. So let's take this plane and imagine different sections. We are still going to get parabolas facing upwards, but they should somehow pass through these points. So here you had a parabola like this. Now imagine this parabola sliding downwards along this parabola. So now I think it's something which is somewhat imaginable. Let me try to sketch it. So as we said, we have a parabola like this. We have a parabola in this plane, and now we start sliding it along this parabola. So we have something like this, something like this. And maybe to try to imagine even better how this whole shape looks like, think now about horizontal sections. Horizontal sections look like hyperbolas. So they look like this, and the second branch goes into the board like this. So horizontal sections look like this. Hyperbolas like this. So let me try to produce a little bit better picture. And then I'll describe in words what is this surface. So something like this. A shape which is curved like this in this direction, like this in that direction. And, well, if you think where you have seen such a picture, it's the shape of a saddle. If you imagine a horse and the saddle on this horse, well, your legs are facing kind of forming a parabola like this. The saddle makes a parabola like this, and you see such a shape. If you cut it by horizontal plane, well, you'll see a hyperbola like this. Okay, so now at least roughly we understand the shape of this surface. Once again, we started with just an equation. Z is x squared minus y squared. It even looked somewhat similar to the previous example. Just one small change. I changed plus to minus. And now I have a completely different shape. And we'll just call this shape, well, a saddle. So, admittedly, it's not a simple task. I mean, there are two complicated things which you should do when trying to imagine the shape of a surface. One thing, which, yes, it is complicated. Cut it by planes. In each of the planes, try to sketch the section. We've seen in this example that some planes are more complicated than others. The horizontal planes in this example were quite complicated. The sections turned out to be some hyperbolas, and well, we weren't quite familiar with hyperbolas, so it was somewhat complicated. Another even more complicated part is, having obtained the information about all the sections, try somehow to fit it together. So the problem here is not really mathematical, it's a problem of imagination. Our brain is not really three-dimensional, it's kind of 2-point-something dimensional. I mean, it's good at the kind of taking a set of two pictures and reconstructing roughly the three-dimensional space. It's not really good at actually imagining three-dimensional objects and manipulating them. So it's not an easy task, well, to take a bunch of sections and fit them together to form some kind of shape. Okay, so maybe any questions about these two examples? Yeah?
Did you consider the downward direction x, that y, that z?
So in this picture I tried to make this to be x, this to be y, and this to be z.
And if you switch those around, what would be some
It will be, well, such a saddle but rotated. Other questions? Yeah?
Sorry, I just don't understand. Is it that trace that creates that saddle? Or that saddle?
So these traces, okay, let me show the traces on the better picture here. So I think this picture is kind of gives an impression of what this looks like. So now think about, let's say, XZ traces. We are cutting by planes parallel to the XZ plane. Well, here's one. It's a parabola. Here's another parabola, another parabola. Different traces. Think about YZ traces. Planes which are parallel to the board. Well, one of the traces, like x equal to 0. Well, you can imagine taking a point here and cutting like this. You'll see such a trace. We're taking a point somewhere over there. And it's such a trace. So you can imagine taking planes like this. As you shift it, you get an inverted parabola, but slides upwards. And finally, the horizontal traces, xy traces. If z is greater than 0, you get such hyperbolas. If z is below 0, you try to cut this saddle by horizontal plane which is below this point, you'll get kind of such a trace. This is hidden, and this we see. So you get something like this, and also something like this. And if you continue this further, you'll see the whole hyperbola like this.
Where on that graph is Z not equal to 0?
So it's this point, and z not equal to 0, well, it's actually kind of funny trace. When z not is exactly equal to 0, the hyperbola degenerates to a set of two lines, like this. And on this surface, you will see a set of two lines, like this. Yeah?
Where did you get those little lines that are on the side again, Lucas?
These ones?
No, the ones that are just, the ones that you just drew in, they're like,
Oh,
they're
these ones?
cutting like the last hyperbola down here. The ones that you just did like tiny little squares.
Wait, these ones?
Yeah, those.
Yeah.
Okay. So I try to cut my saddle by a plane, but I try to make the plane be below this point. So imagine you have a saddle, and you're cutting it by such a plane, so I get a section like this and a section like this. So two disconnected
That was
parts.
just formative hyperbola, right?
Mhm.
Oh.
So yes, it is true that this thing is a complicated shape. Yeah. So it is a complicated shape. It's not obvious from kind of our imagination that this plane, that this surface contains any lines at all, but it does. It contains, let's say, two lines in this point. But it isn't, well, it is some shape, it is interesting, and we'll see later that it's also important for us. But it will come later.
This is something that you can ask us in the exam if you draw like a shape.
So to be honest, I right now have a hard time imagining a question which will be kind of manageable enough and about this topic to be asked in an exam. But you should at least understand that it's possible in principle. Okay, let me give you one kind of exercise here. Another important example of the surface. Example, but I will not show all the traces. I'll just talk about this surface. X squared plus y squared plus z squared is equal to 25. Well, you can try to cut it by different planes and see what you get in the sections. Maybe some of those are quite easy. Let's say the horizontal section at height 0. When z is equal to 0, just imagine setting z equal to 0, you'll see x squared plus y squared is 25. What is it? A circle of radius 5. So on this plane, you should imagine a circle. Another section, let's say y equal to 0, so such a section. And xz plane, x squared plus z squared is 25. Once again, circle of radius 5. So you should imagine something like this. Let's say x equal to 0, also quite easy. Y squared plus z squared is 25. Once again, a circle, but now on this plane. So I think you start seeing what this might be, and yes, it is a sphere. It is just the surface of a ball. If you look at other sections, well, other traces, you see that they are circles, but with slow radii. So all the traces are circles. I did not perform the computation. I leave it as an exercise. The shape is, the surface is a sphere, radius 5, center 0, 0, 0. And with our knowledge about vectors and lengths of a vector, it's quite easy to see that it is indeed the equation of a sphere of radius 5. How would you describe a point on a sphere of radius 5? Well, it's a point whose distance to the origin is exactly 5. What is the distance to the origin? It's, if you have a point x, y, z, kind of vector from 0, 0, 0 to x, y, z, what is the length? Well, it's square root of sum of coordinates, sum of squares of coordinates. So square root of x squared plus y squared plus z squared is equal to 5. This is exactly the length of the vectors of x, y, z. So it's a set of all points, set of kind of all arrows whose length is equal to 5. So it describes the surface of a sphere radius 5. So admittedly, I did not perform the computation with the sections. I just, well, performed the trick, but still, you can understand what this equation is describing. And of course, all these examples are just the simplest possible examples of surfaces. I mean, yes, this surface was a little bit more complicated than the others, but you can imagine that if you write just slightly more complicated equations, I don't know, instead of y squared, write y cubed, you'll get vastly more complicated surfaces. They will have some folds, they might have self-intersections, so you might imagine quite complicated surfaces. Of course, we are not going to deal with all those complications. We'll stick with simple examples. Okay, so next question is, well, why did we torture our imagination with all these surfaces? The answer is because we want to understand later functions. So we'll start with functions of just two variables. A quantity which depends in some manner on two other quantities. So what is a function of two variables? Well, it's just is function takes in two numbers and outputs one number. So it's a recipe how to take two numbers, do some manipulations, and output a third number. Examples. Here's a function of two variables. Takes in x and y, outputs their product xy. So So this function is, well, the multiplication function. It takes two numbers and multiplies them. Another function, g of xy, is, let's say, pi x squared y, where pi is not a variable, it's the number which is approximately 3.14. So here's a function does a little bit more complicated thing. Takes x, multiplies it by itself, multiplies it by y, and multiplies the result by the constant pi. Once again, it takes two numbers, outputs a third number. It might have actually come from, well, from somewhere. Maybe it is the function taking the radius and the height of the cylinder and outputs spitting out its volume. So maybe you actually have seen such a function once. If x is the radius of base of the cylinder and y is the height, the volume of the cylinder is a function of this radius and the height. And it's exactly this function. Take the radius squared, multiply by the height, and multiply the result by pi. Well, it could be more complicated. It could be something like y sine of x plus x cosine of y. Could be lots and lots of different functions. The only thing which is common is, well, they take in two numbers, output one number. We call such a creature a function of two variables. Okay, so we have functions of two variables. We want to, once again, understand them somehow, understand the behavior of this function. With the function of one variable, we had a trick. It was graphing function. Take a function, maybe a formula, and produce a graph. On the graph, you see the important features of a function. Where is it the largest? Where is it the smallest? When the rate of change is kind of zero? When does it change very, very fast? When does it go to infinity? If you just look at the picture, you understand quite a lot about the function. What can we do with a function of two variables? Well, we'll see two different ways to visualize a function of two variables. First way is basically the same way. Produce a graph. So the graph of function fxy is the surface z equal to fxy. So what you do is, well, imagine xy being the plane of the floor, and then you imagine that my function describes the height function above the floor. So if at this point xy the function is equal to 1, we'll measure 1 meter from the floor. If at this point it is 2, measure, well, 2 meters from the floor. And above each point of the floor, you'll see some point of your surface. And together there will be some surface. On this surface, once again, you will see some important features of your function. Maybe you'll see a hill on such a surface. You'll see a local maximum. You'll see kind of valley, a local mean. You see, well, at some point, the whole surface goes to infinity like this, like goes above the ceiling and all the way to the sky. They're all kind of asymptote. So if you see such a surface, you'll know quite a bit about the function. The only problem, once again, is three-dimensional thing. It's not that easy to imagine, it's not that easy to draw. But luckily we do have some examples ready for us. So let me just give one example. Graph of f of xy, which is x squared plus y squared. What is it? Well, it's a surface z, which is x squared plus y squared. Maybe not that easy to understand what it is from the first sight, but we already made the effort. We already know what it is. It's a paraboloid. So here's the graph of this function. If you are given a point xy, you'll find out what this function is by just taking a vertical line and seeing what is the height of this paraboloid above the xy plane. Okay, so next time we'll talk more about the functions, and once again we'll start with the quiz, so please register your clickers.